Audio Jungle. Audio Jungle.
So now we have velocity triangle, okay, for axial flow turbine, and the common velocity triangle you have seen for the inlet and exit, okay. So for the practice, multiple times you have to draw, and you have to practice velocity triangle for the axial flow compressor separately, for axial flow turbine separately, and at the same time for the centrifugal compressor also, okay. All right. So like here you had seen, this is suppose this is the blade here, see. Okay, this is the blade, and if you check the flow will be, obviously inlet will be the absolute flow. This is what C1, and this will be CA1, and this angle will be alpha 1. Okay, and this is nothing but nozzle, or you can say stator. Then this flow will go to the next, which is nothing but you can say it's a inlet for the rotor. So this is the inlet for the rotor. This is what rotational speed. Okay, and from the axial, okay, I will draw that, and this is what all right, this is nothing but uh, tangential relative velocity, which is nothing but omega 2, okay, and this will be the absolute velocity, which is nothing but C2. And now here we have a rotor, okay, this is the rotor blades. Okay, okay, this is the rotor blades here, and the flow will be entered with the relative velocity for the rotor. And this rotor is what moving, rotating, okay, and now the exit from the rotor will be with the relative velocity. So again you will get this relative velocity like this. Okay, all right, so this is nothing but u, this is the exit relative velocity from the rotor, so which is nothing but omega 2. This is the absolute velocity, which is nothing but, sorry, this is the omega 3, this is the C3. Now if you check the axial components, so obviously this will be the axial component, okay, and this will be the CT3. Similarly here, from the axial, this relative velocity angle will be beta 3, and from the axial, this will also, you can write, this is the alpha 3, okay, and from the axial, this will be what, alpha 2, and from the axial, this is the beta 2, okay, and obviously this value will be the whole from here to here. This is what, CT2. So this velocity triangle what I have drawn here, and obviously this will be the axial velocity CA2, and here also this one will be the CA3. For the axial machine, CA1 is equal to CA2 is equal to CA3, that you know. So whatever the alpha 1, beta 2, alpha 2, beta 3, everything, whatever the angle I have given and all the components, velocity component, whatever I have given, it is similar to this one, okay? What you have seen the velocity triangle earlier, huh? So it's same only. The thing is, most of time the velocity triangle they are giving different manner, so that time you should analyze. So that statement I had given, if you remember, that air angle, which is nothing but alpha 1, alpha 2, alpha 3, it is the angle of the absolute velocity from the axial. So this velocity triangle what I have given, I have taken alpha 2, beta 2, and this is the axial component. From here I have measured, and similarly alpha 3 and beta 3 I have measured from the axial. This is the axial velocity, and from here we have measured. So remember, alpha 1, alpha 2, alpha 3, these are the air angle, and it is measured from the axial component or axial velocity. Similarly beta 1, beta 2 and beta 3 are the blade angle, and it is measured between the relative velocity and axial components. And alpha 2, alpha 3, these are the angle between the absolute velocity and axial velocity component, okay, from the axial direction. So this velocity triangle and this velocity triangle what I have drawn here, it is same, there is no difference. The thing is the different manner they have used to draw. So all type of the, at least you should have a proper visualization. Whatever the velocity triangle they will give to you, you can identify, and you can use the formula based on that. Sometimes they will change the angle, okay, so whatever the required angle you can write by your own, no? I mean, suppose somewhere it is measured from the horizontal side, and it is measured from 30 degrees. So for from the vertical side it will be 90 minus 30, which is 60. So accordingly you can change also. So for that reason this triangle I am giving. Now this one you can combine, and if you combine this triangle, then one more triangle you will get, and it is the combined inlet and exit velocity triangle. So it will help you while you are solving the problem. So I will draw this also, okay. Now so this is the combined velocity triangle, and it is nothing but this is the one horizontal component here, okay, sorry, this one, all right. Now this is the line which is indicating the axial component, the magnitude of axial component, all right. Now we'll draw the relative as well as absolute velocity component. So connect this triangle and you will get it. So this will be this is nothing but the absolute velocity, okay. This will be C3, absolute velocity, okay. And next will be the absolute velocity here. This is the another velocity, absolute velocity for the inlet velocity triangle. Okay. Now we can have this is the relative velocity, which is nothing but W3, and this is the relative velocity for the inlet triangle. Okay. And obviously this one is CT3, CT2. All right. Here. Fine. Now this is what U, and this value will be what? It is nothing but delta CT. What is the delta CT? You can say it's CT2 plus CT3. All right. So this is what the velocity triangle, and if you want to calculate the work, then you will write the specific work. We already have derived. We are not going to derive, but if you want to write, you can write U into delta CT, which means U CT2 plus CT3. This is the turbine work. So this combined velocity triangle you need to remember. Now you write the angle. Okay, from the axial you had seen that angle, from the axial we have written. Okay, so now this is the combined triangle if you want to draw, because if you check this part here, this part this will be the exit triangle, and this will be the inlet triangle. So in short, you can understand in this way. Okay, and all the component here, like angle if you want to write. So this is what? This is the axial. Okay, so it's your choice what velocity triangle you want to use. Now C3, this is the angle from the axial. C3 is the angle alpha 3. This is the W3, and from the W3 this angle will be beta 3. From the axial I am saying beta 3. Similarly, this W2, which is the relative velocity, from the axial what is the angle? Beta 2. This is the C2, so from the axial what is the angle? It is alpha 2. Alright, so this is the velocity triangle. So it's your choice what velocity triangle you want to use. Alright, I hope this one is very clear to you. Anyway, so this one is the velocity triangle, and already we had seen the simple one velocity triangle also, that I already told you I have followed veganation basically. So that velocity triangle also you can prefer, it's your choice only. Okay, what velocity triangle you want to prepare. All right, so now I think the most of things I have covered. Now we'll go for the next, which is nothing but degree of reaction, which is very important in this turbine. Okay, so if you read the degree of reaction, so for the compressor you had seen, for the compressor you had written degree of reaction, and there was the rise, enthalpy rise. Okay, so here we will have expansion, so hence we will have enthalpy drop or temperature drop. So degree of reaction, you know the formula, okay, for the degree of reaction. So next, so I must write degree of reaction, which is denoted by capital R. Okay, degree of reaction. So I told you in compressor the same thing for the turbine also we will have, like this is what a nozzle, and this is what rotor. So in the nozzle and rotor we will have expansion. Okay, so because of the expansion we will have a drop of the enthalpy. So it is the sharing of the drop of enthalpy between nozzle and rotor, like what percentage of nozzle is what dropping enthalpy, and what percentage of rotor is what dropping the enthalpy, or expansion takes place in nozzle and expansion takes place in rotor. That contribution basically you have to check with the help of degree of reaction. All right, so so it is defined as, it is defined as, because many things I have explained for the degree of reaction in a compressor, so I'm just taking a shortcut for this because already you know that definition and all. So formula I will write. So it is defined as R is equal to enthalpy drop in moving blades. So what is the moving blades? It's a rotor. Okay, so I can write here enthalpy drop in moving blades divided by enthalpy drop in the stage. All right, so basically it will show the fraction, the stage expansion which occurs in rotor, and it's usual to define the terms of static temperature drop also. Okay, so as I told you, it will show the contribution of the rotor as well as the complete stator, or you can say stage, because if you say stage then stator means nozzle and rotor both will come. So this shows the fraction of the stage expansion which occurs in rotor, and it is usually to define in terms of static temperature. How we can write in terms of temperature? We just write this enthalpy in terms of temperature, so you will get it. So here this R is nothing but, finally you got, if you check this number is 1 2 3. So what is the enthalpy? If you check, this is what a TS plot, and if you check, this is what basically uh, you can say it's a basically 1, and somewhere if you draw, this is 2, and this is what 3. 1 2 3. So based on this you can draw. Okay, this is the expansion, so this expansion will be like this. Check this properly. So if you check between 1 to 2, this is the 1 to 2. So 1 to 2 is what separate here you can write. 2 to 3 is nothing but rotor, and 1 to 2 is nothing but nozzle, and 1 to 3 is nothing but stage. Okay, this I can say this is 1, this is 3, this is 3 dash. Okay, anyway, so if I will write what is the degree of reaction in this case, so whatever the static enthalpy drop in rotor, so where is the rotor? Rotor is between 2 to 3, so static drop, which is nothing but H2 minus H3 divided by the stage. So where is the stage? Static drop is nothing but H1 minus H3. This is the, and if you want to write in terms of temperature, so it is what Cp T2 minus Cp T3 divided by Cp T1 minus Cp T3. So this is nothing but T2 minus T3 divided by T1 minus T3. This is what degree of reaction. Okay, so as you know very well, similarly we had done in compressor and we had derived this. So here I am not going to derive, truly saying not required derivation. In compressor already I have derived, so I believe that in the with the help of that compressor derivation, that hint you will get, and if you want you can derive by your own only. Now I'm just going to write this degree, because this degree of reaction in terms of enthalpy as well as in terms of temperature, same thing you can say it is the drop of the static temperature in the rotor, and drop of static pressure in rotor divided by drop of static pressure in stage. That formula also is what you can write in terms of static pressure drop. Anyway, and second thing, the very important the formula of degree of reaction in terms of the angle, and that angle is very important. So derivation, as I told you, it is not required. Okay, generally here in 2-3 steps required. If you say I will write, otherwise I directly I will give the formula here. Okay, because if you check the 2-3, what is the 2 T2 minus T3? So if you write in terms of temperature formula or that steady flow energy equation, if you use, then you can get the relation between T2 and T3. So, and what is the T1 minus T3? It is the, if you multiply with the Cp, so it will be the work only. Yes or no? So here you can write this one, assuming the axial velocity is constant. Wait, 2-3 lines required only, so I will write here. So you know that CA1 is equal to CA2 is equal to CA3, and it is CA is equal to constant, that you know. And inlet and exit flow will also, absolute velocity will be same, that is the inlet is equal to exit from one stage, inlet and exit for complete stage. Okay, so C1 is what will be equal to C3. Now if you check what will be the work is nothing but Cp T naught 1 minus T naught 3. This is the stage work, and this you know very well. You can also write Cp T1 minus T3. So if you check in denominator, it is Cp T1 minus T3. So this is what? This is the work, specific work. Okay. So this is nothing but work, and this in terms of angle you can write UCA tan beta 2 plus tan beta 3. This is the value of denominator, and if you go for the numerator, so you can write that value, which is nothing but the basically enthalpy. And what is the enthalpy across the rotor? It will be the a relative enthalpy. What is the relative enthalpy? H naught 2 is equal to H naught 3 relative. Okay, this is across the rotor. So what is H naught 2? If you remember, it is nothing but H naught 2 is what? H2 plus velocity. What is the H2? It is Cp T2 plus. What is the velocity? It's a relative velocity, and relative velocity is nothing but omega 2 square by 2. Similarly here, this is what? Cp T3 plus H3 plus a velocity component. What is the velocity component? Because it's a relative, so omega 3 by omega 3 square by 2. And you know very well, if you solve this value, so you will get it from triangle. Now from this triangle, if you check this velocity triangle, you can get the value of velocity. Okay, what will be the value of velocity? If you see here that cos beta 3, what will be the cos beta 3? If you check, so cos beta 3, if you calculate, then it will be, or the previous triangle what you have already, that previous triangle already I have given, and their velocity triangle, if you open, then you will get cos beta 3. So what will be the cos beta 3? It will be the Ca divided by omega 3. Similarly, you can, because we have a in terms of beta, so similarly we can write cos beta 2. So if you write the cos beta 2, so cos beta 2 will be Ca divided by omega 2. If you place this, check the triangle and you place this value, so you will get what you will get here. Check, you will get final that result I will write here. You will get Cp T2 minus T3, you will have 1 by 2. Check the bracket, it is uh, omega 3 square minus omega 2 square. If you write all those things, so what you will get? You will get 1 by 2. You write the angle omega 3, so it will be sec square beta 3 minus it is sec square beta 2. Check that. So based on this, you can use and you can write this value. So finally you will get it, and if you solve, then you will get 1 by 2 Ca square. You break it in tan, so what you will get? Tan square beta 3 minus tan square beta 2. So what is the degree of reaction? R. This is Cp T2 minus T3 divided by Cp, stage is T1 minus T3. If you combine this, so what is the Cp, this value? This is what? 1 by 2 Ca square. If you open this bracket, so what you will get? Tan beta 3 minus tan beta 2, and next bracket tan beta 3 plus tan beta 2. Okay, divided by what is the Cp T1 minus T3 for the stage? It is work, and it is UCA tan beta 3 plus tan beta 2. So it is UCA in bracket tan beta 2 plus tan beta 3. Now you got the derivation also. So I told you it's only 4-5 lines only. It's your choice. This value will be cancelled out. So you check what you will get. Finally, R is equal to I think it is Ca by 2u in bracket. What you will get? Tan beta 3 minus tan beta 2. This is the degree of reaction. Anyhow, you need to remember this final result, okay? Because gate question they are asking based on it. If you know the formula, you can hit the question directly. Okay, so this is what degree of reaction for the axial flow turbine. So I told you they just like in compressor degree of reaction, basically three formulas was there. So the same three formula for this also I just want to write, because each and every formula we cannot derive, it will take time. Here just for idea only I have derived this. Rest formula I am just going to write, so please check it. So first, just now you have derived this is R is equal to Ca by 2U. You got tan B3 minus. This is the first formula. Second formula, remember all three formula required. Okay, 1 minus Ca by 2U tan alpha 2 minus tan alpha 3. Third formula is, you need to remember, okay? If you derive, it will come. For compressor, I have derived, so here in turbine, I am not going to derive. You please check it. Tan alpha 2 minus.
So this
tan
degree
beta.
of reaction, this.
So this is the formula. Tan alpha 2 minus tan beta 3. No? Sorry, now it is correct. Tan alpha 2 minus tan alpha 3. Yes. So all three formula you need to remember. It is very special actually. Okay. And anyhow, you need to mug up this formula. All right. Now, so based on this, we have a different type of turbine, okay, like impulse turbine and reaction turbine. Just for compressor, a reaction machine, impulse machine, 50% degree of reaction. So all those things I explained you. So similar thing we can do for this also. Okay. Now check. So types of axial flow turbine. So basically we have two types. Okay, we have two types of the turbine here. First one is impulse turbine and second one is reaction turbine. In compressor only I had explained what is the impulse turbine. If a degree of reaction is what 0, then it will be called as a impulse turbine. So I'm not going to give so much definition. It is already explained in compressor. So in short I'm giving. And reaction turbine, if the degree of reaction is what 100% or in number it is 1. Okay. Then it will be called as a impulse as well as reaction turbine. Okay, all right. Now you check the formula here. Okay, check the formula. If R is equal to 0, then what will happen? If R is equal to 0, if you equation 1, this is equation 1, this is 2, and this is what 3. So what you will do, you check. So from equation 1, what you will get if you keep this value R is equal to 1 in equation 1, then what you will get? Check. You will get see R is equal to 1, then this value will be 0. So tan beta 3 is equal to tan beta 2, or you can say beta 2 is equal to beta 3. This is the mean of the impulse turbine. Okay, so this is the one thing. Second thing, if you know, uh, this is the one part of it. Second part of it, if you check, what is the degree of reaction formula? Degree of reaction formula is, check the formula here. Formula only I am saying. It is the enthalpy drop in moving blades. What is the moving blades? It's a rotor. So you can say enthalpy drop delta H in rotor divided by delta H enthalpy drop in stage. That's the mean of it. So if R is 0, it means that rotor value will be 0. If rotor is 0, that means what? There is no enthalpy drop in rotor. There is no enthalpy drop, or you can say there is no expansion in rotor. That's the mean of it. So R is 0, that means enthalpy drop in rotor divided by enthalpy drop in stage. So what is the mean of it? Its mean is very clear. Delta H will be 0, delta T will be 0, and delta P will be 0. That indicates what it indicates. It's indicating it's indicating no expansion in rotor. That's the mean of it. You remember, okay? In very short I am going, because everything I have explained on full scale in compressor. So same thing I don't want to repeat here. In short I am just telling you, okay? Now coming to reaction turbine. So for this reaction turbine, if you check the equation, R is equal to 1. If you keep R is equal to 1, then this 1 cancel out. So what you will get? Alpha 2 is equal to alpha 3. Yes or no? If you check here, so what you will get? Yes. So from equation 2, what is the equation 2? If you keep R is equal to 1 cancel out, so you will get alpha 2 is equal to alpha 3. This value they are asking in exam, okay? They are asking in exam. Alpha 2 is equal to alpha 3. Anyway, now what is the second thing? If R is equal to 1, then it means in stator or nozzle, in nozzle there is no expansion. That's the mean of it, because rotor divided by stage, and in stage what is the formula of it? If you check, what is the degree of reaction? It is change of pressure or temperature drop. Okay, temperature drop I must write now separate, in rotor divided by temperature or enthalpy drop in rotor plus temperature or enthalpy drop in stator. This is the actual formula, and this formula I had given in compressor. So same thing it will be for the turbine also. In compressor it was rise of enthalpy, rise of temperature, rise of pressure. In case of turbine it is the drop of temperature, drop of enthalpy, drop of static pressure. Okay, but the meaning will be same. Only in case of compressor it is rise, in case of turbine it is fall or drop. So check, if R is 1, that means stator contribution is 0, then rotor by rotor will be 1. Yes or no? So it means the direct this result I will write. It means there is no drop or no expansion takes place in stator. That's the mean of it. We can say no expansion, no expansion in what I have written here, no expansion in rotor. That is true. This is for rotor. Okay, everything for the rotor here need to write. All right, and now R you will get when there is no expansion occurs in nozzle or stator. All the expansion occurring in the rotor part only, called reaction turbine. This one is, I think, clear. Okay, so this is the very small one slide I have explained all the concept behind the impulse turbine and reaction turbine. What are the variation of the components? I mean, component in the sense angle wise, and that rotor and stator contribution, all those things here it is explained nicely. Okay, in short. Now the most desired degree of reaction is what? 50%, as I told you. So that I will explain separately. In turbine, many times they had asked question. Okay, I mean, in one day exam, I'm not talking about GATE aerospace only, whatever the one day exam related to the this aerospace or propulsion. So they are asking question, MCQ question for the impulse turbine and reaction turbine. So impulse turbine, it came immediately, it should come in your mind, it is R is equal to 0, which is degree of reaction 0. And if degree of reaction will be 0, then what will be the relation of the angle? So immediately it should come in your mind, it should be beta 2 is equal to beta 3. This is when there is the impulse turbine. And if it is reaction turbine, immediately it should come in your mind, R is equal to 1. When R is equal to 1, then you put this value in equation 2. So if you put in equation 2, then what relation you will get? Alpha 2 is equal to alpha 3. This result you should come in your mind. And second point, which is very important, this is first and this is the second. Similarly, this is the first and this is the second. Okay, so all those things you need to remember. Anyway, now we'll go for the next. What is that? This is very special, very important. 50% degree of reaction. So if I say 50% of degree of reaction, then what is the mean of it? So its meaning is clear. R is equal to 1 by 2, that is the 50%. Okay, if you keep this value in equation, check which equation you have to keep this value. This value you need to keep in equation number 3. So if you keep this value in equation number 3, then 1 by 2 cancel out. So in equation 3 if you do, then what you will get? You will get angle. Let me check. 1 by 2 cancel out. It's alpha 2 is equal to beta 3. Yes or no? So here you will get two things. This is nothing but R. R is equal to whatever the drop because of rotor, plus because of stator or nozzle. It's your choice what you want to write. Okay, so if it is 1 by 2, then what is the mean of it? Its meaning is check, its meaning is delta H in rotor, whatever the drop of enthalpy in rotor is equal to drop of enthalpy in stator. What is the mean of it? Its meaning is very clear. It is the equal contribution in expansion. Okay, so both components are having expansion. Both component means rotor and stator. So equally distributed load. Okay, now this is the one thing. Second thing, what is the angle wise? What is the angle wise meaning? Angle wise meaning is, check if third equation, R is equal to 1 by 2. So right and left both side 1 by 2 we have. It is cancel out, then finally we'll get alpha 2 is equal to beta 3. So you will get this value. alpha 2 is equal to beta 3. So alpha 2 is equal to beta 3. This is the one thing. Second thing, also because you know very well what we have relation tan alpha 2 plus tan alpha 3 for the turbine, it is equal to tan beta 2 plus tan beta. This we have derived in last class. So if alpha 2 is equal to beta 3 means tan alpha 2 is equal to tan beta 3. That's the mean of it. Then it should be tan alpha 3 is equal to tan beta 2. It means you can say it is alpha 3 is equal to beta 2. That's the mean of it. Yes or no? Both if you check. Now what this indicates, alpha 2, where is the angle of alpha 2? If you check in terms of the velocity component in compressor, I explained. So alpha is the air angle which relates to the absolute velocity. And what is the absolute velocity component in tangential format? It is, if you remember, it is CT2. And for the tangential velocity, in case of the relative velocity component, it was WT3. So it is, because it is beta 3, so it is WT3. I have explained in compressor, please go and watch it, so you will get it. Okay, I am not going to explain this again because it will take time. You go and watch that previous compressor lecture, so there nicely I had explained this. Okay, this is all. This is very important here, and they are asking in GATE. Okay, this question is like whatever I have mentioned here, it is very important. Check this box. This box is very important. Okay, and this is for 50% degree of reaction. This is very important. You please check it. All right. So what is the very important point came here? The important point for the 50% of degree reaction, first of all, its meaning is R is equal to 1 by 2. And if you check in equation 1, equation 3, if you keep this value, then what you will get, sorry, this is 1 by 2, not 1. Sorry, I made mistake. R is equal to 1 by 2. Now fine. So if you, when you will get 1 by 2, when in numerator and denominator, for the rotor and stator both are having the same distribution, I mean same expansion. So same value for the rotor and stator if you have, then it will be added. So it is 1 plus 1, 2, and in numerator obviously it will be 1. So 1 by 2, you will get that. So, and this is the mean, actually physical meaning of the 50% degree of reaction. And what is the relation angle wise and velocity component wise? So this is the relation. How, from where you will get this alpha 2 is equal to beta 3 from this equation 3. If you check this equation 3, you will get this result. So I think it is now very clear. Okay, for the all the degree of reaction you have seen, degree of reaction when it is 0, when it is 1, and when it is 50%. And this 50% degree of reaction is very desirable for any turbo machinery. It is compressor or it is turbine, doesn't matter. Why it is desirable? Because the work here, if you check in terms of enthalpy drop, in terms of temperature drop, in terms of pressure drop, both are doing the same work, actually same contribution for the rotor and stator we have. So it is equally distributed. So the burden is what distributed to both component. Okay, the same, whatever the amount of work doing by the rotor blades, so same thing it is done by the stator also. So work, you can say, it is equally distributed. So both are the same burden load. Okay, so for that reason, any turbo machine what we have, it is compressor or turbine, 50% degree of reaction or approximate to 50% degree of reaction is what desirable. All right, now this is the one thing. All right, so now we'll go for the performance parameters. So performance parameter for the FT. What are the performance parameters? If you check, these performance parameters are nothing but, these are the basically two. We have these performance parameters are flow coefficient flow coefficient. Okay, then we have a blade coefficient, and third one is the speed ratio. Same thing we had seen for the compressor also. And if you go for the flow coefficients, it will be denoted by phi. Okay, and blade coefficient, if you remember, it will be denoted by psi, and speed ratio, if you go, it will be denoted by sigma. Okay, it will be denoted by sigma. So now first we'll go for the flow coefficient. So flow coefficient is nothing but, if you remember, it was defined in compressor also. So flow coefficient is basically, it is defined as the ratio of inlet velocity. Okay, ratio of inlet velocity, and what velocity? Axial velocity. Ratio of axial velocity to rotational or blade speed. What is the blade speed? U. What is the axial velocity? It is CA. So what is the phi? Phi is nothing but CA by U. It's a very important parameter. Okay, very important parameter. This is what? Flow coefficient. CA divided by U. It's a CA divided by U. Okay. And this type of parameter basically used for the designing of the turbine. Okay, designing of the turbine. And now next parameter what we have, it's a CA by U, you know that, but sometimes this flow coefficient also, if they have, anyhow, if you don't know CA and U and they have asked flow coefficient, but the angle they have given to you, alpha 2, alpha 3, beta 2, beta 3, all those things they have given to you. So how to get that? So if you remember, what you got, in the triangle, if you recall the velocity triangle, so what was the triangle? The triangle was CT2 plus CT3 is equal to WT2 plus WT3. Yes or no? And actually you got U is equal to, you got from the velocity triangle, from inlet exit velocity triangle. So if you recall that, so what you got that time? CT2 minus, check the velocity triangle. From the velocity triangle I had given this result, WT3 minus CT3. Okay, this was given to you, and here also it was explained like U is equal to CT2 plus CT3, and this value you can write, which is nothing but, because both are the same thing, so this value also you can write WT2 plus WT2. So here you got that U by CA. If you write this, so it will be tan alpha 2, tan alpha 3, or tan beta 2 plus tan beta 3. If you recall this, then you will get it. So if you write the flow coefficient, so what is the phi? Phi is nothing but Ca by U. Okay. So if you write this value, then what you will get? You will get the value of this is the value of flow coefficients. It's your choice. If they have not given angle, then the velocity component you can use this, and you can write in this format also. All right. Now, so next is what the next parameter what we have here. It's a blade coefficient. So 0.2. So the blade coefficient in the compressor, I told you this is also called temperature drop coefficient, if you remember. Temperature drop coefficients, or this is also called, very important, loading coefficient. Loading coefficients. Okay. What is the formula or how it is defined? So it's defining by the basically the blade loading coefficient is used to express work capacity of the stage. For what it is using? Why this performance parameter you are using? It is used to express work capacity of the stage. Remember it, okay? Of the stage. And what is this parameter? This parameter is what basically designing parameter. Okay, it's a designing parameter. Now, so what is the formula for it? So if you remember that compressor also, it was explained the same thing. So it was the total work input in case of compressor, but here whatever the work is what produced or generated divided by the square of the rotational speed. So it is nothing but psi is equal to whatever the work produced divided by square, which is the rotational speed square. This is nothing but the what it is called temperature drop coefficients or loading coefficient. What is the W? If you remember, it was UCA in bracket. What was the work in case of the turbine? If you remember in case of turbine, what was the work? So it was UCA tan alpha 3, okay, divided by, so psi is equal to, you can write Ca by U tan alpha 2 plus tan alpha 3, or in terms of beta also you can write Ca by U. What is the tan alpha 2 plus tan alpha 3? It is tan beta, sorry. It is tan beta plus tan beta 3. And why this parameter will be used? This parameter will be used to express the work capacity of the compressor for the stage. So this loading coefficients, basically this is called loading coefficient, okay, or it sometimes also called blade coefficient, Okay, so in terms of angle also here it is explained, so you should remember it. The last one is the parameters which is called blade speed. This is also very important. Okay, so remember blade loading coefficient, also called temperature drop coefficients. No? This thing should be very clear. So next is the speed ratio. Okay, so how you will get that speed ratio? So it is the ratio of the rotational speed to the absolute speed. Okay, absolute speed of what? Whatever the absolute velocity or speed is there in inlet triangle, which is nothing but C2. Okay, so I will write this, it will help you in numerical. So blade speed or speed ratio. Okay, so it is denoted by sigma, as I mentioned already. It is the ratio of blade speed divided by absolute speed, which is nothing but C2. Okay, so you need to remember this value, and if you write this in terms of angle, so that also you can do. Okay, with the help of angle also you can write, I mean that velocity and angle sine rule if you apply in the triangle. So if you check the triangle here, so sine rule if you apply for this triangle, in fact this triangle, and in last class what I had drawn one more triangle, both triangle will help you. So for this triangle as well, if you write, then what will be the angle in front? Okay, uh, so it will be the u divided by, check this inlet triangle here, so it will be u divided by sine alpha 2 minus beta 2, and where is the C2? This is what C2 here, see, so this is the C2. So if you write the C2, so this angle will be what? 180 minus 90 minus beta 2, right? So I will write here, the apply, you can apply from the inlet triangle, so you will get it. No? It is called, you might heard in 10th standard mathematics, sine cosine rule. So this is the sine rule basically, and if you apply here, so it will help you in numerical basically. So what will be the u? So here this you can write u divided by, from the triangle, inlet triangle, sine alpha 2 minus beta 2 is equal to, this also you can write, check u upon sine alpha 2 minus beta 2, in front of u component what is the angle? Sine angle. No, basically you need to take sine angle in sine rule. So sine into this angle, it is alpha 2 minus beta 2, and similarly you can do for the C2. So in front of C2 it will be 180 minus 90 minus beta 2, you can do, or you can use that previous triangle also, that what I have given already. No? In previous class one more triangle I had given. So which one is better, you can prefer any triangle, you can prefer both. Three triangle I have given in three ways, you can use any one and you will get your answer. Okay, so this one will be C2 divided by sine of 180 minus 90 minus beta 2. Okay, so you may write this, what will be the u upon C2? You can check u upon C2, if you write, then u upon C2 will be sine alpha 2 minus beta 2, right, divided by, if you check this value, if you solve this, sine 180 minus this, minus minus plus 180 minus 90, it will be 90 plus beta 2, so sine 90 plus beta 2, it will be cos, no? So you will cos beta 2. So finally this formula you need to remember, this formula you will numerical point of view, this is very important. And from where you will get this? From inlet triangle, you apply sine rule. Okay, then you will get it. All right, so these are the performance parameter. Now the last what you are getting, it is the basically the free vertex design for the turbine. So there we have the points for the free vertex design, and formula when you have suppose root radius you have, so and mean radius if you have, then tip radius you can calculate. Similarly, at least mean radius is what known, then with the help of diameter and this free vertex design calculation you can get the another radius. Okay, so this is actually it's very lengthy, but the main conclusion I will give to you. So free vertex design, free vertex design for AFTs. Okay, so we have a points that conclusion I will give, otherwise this one is very long and we cannot enter in that. So see what we have concluded, or what we have pointed out earlier, we had seen the velocity triangles, and it is varying from root to tip of the blade, because whatever the velocity at root, it will not be same at the tip, it will be different. So actually it's varying, so it's vary from root to tip of the blades. Okay, and remember, whatever the velocity triangle we had drawn, we are considering mean radius, and for the mean radius we had drawn the velocity triangle, but actually it is varying from root to tip. So for each and every point we cannot draw the velocity triangle. So whatever the velocity triangle we had drawn, it is for the mean radius. Rest always remember from root to tip, not for turbine, for the compressor also. Root to tip, the velocity triangle is what changing. If somebody will ask to you whatever the velocity triangle we have drawn, it is for the root blade or it is tip blade, so you have to say it is for the mean blade. Means for the blade we are taking average, and for the average we had drawn the velocity triangle. So whatever the velocity triangle till now you have seen in compressor as well as in turbine, it is for the mean blade. Okay, first thing you very important you need to remember. And that velocity triangle varies from root to tip of the blades, because obviously the blade speed u is not constant and it is varying from root to tip. Definitely, why? Because root to tip, why u is what changing? Because diameter will be changing. If you are taking at the root means hub, so hub diameter will be different. In first lecture, previous lecture I had explained hub radius, so hub diameter will be there. So for hub diameter u will be different, because what is u formula? U is pi dn by 60. If diameter is changing, u will be changing. If u is changing, then overall the velocity triangle will be changing. So we have taken an average u, which is called u mean. So for u mean we had drawn the velocity triangle. This is very important. Okay, so so now for the twisted blading designed to take account of the changing gas angles is called vertex blading. Okay, and now for the vertex blading we have a momentum equation. Okay, as for compressor as well as for turbine, we have the momentum equation. Okay, and this momentum equation for the axial machine, it is axial compressor or axial flow turbine. So that equation is called as momentum equation, and this momentum equation is what comes for the vertex blading. Okay, vertex blading. So in the vertex blading we have conclusion, and that conclusion point I am going to write, because this derivation itself a very big only. Okay, and it is most of those who have attended from the starting my class. Why it is called free vertex design? Because two types of vertex we have: force vertex and free vertex. Okay, so in free vertex it was there that velocity is what reciprocal to the radius. And here also, if you go for the analysis, then you will conclude that velocity and radius. What velocity? It's a whirl velocity. So velocity and radius are reciprocal and it is in free vertex, hence it is called free vertex design. Why it is called free vertex design? I will write the conclusion and from there I will explain you why it is called free vertex design. Okay. So conclusion point here I will write here. It's a complete derivation, full package, but not required here. Okay. So the conclusion point I am going to write. So if you check conclusion, what we have in free vertex design, it's points. What are the points? I will write here. All right. What we concluded first, we concluded that the swirl velocity, which is just inversely proportional to the radius, or we can say it's a that velocity which is nothing but swirl component, and this is also Ct into R is equal to constant. This is the conclusion actually. Okay, this comes from the derivation. I don't want to draw that, derive that. So what is the mean of its meaning is that swirl velocity or Ct, swirl velocity is inversely proportional to proportional to radius. And this is what, if you remember, this is nothing but two types of vertex I had explained: force vertex in fluid mechanics, incompressible aerodynamics lecture. If you watch, then you will get incompressible aerodynamics. If you watch, then you will get types of vertex, and there I had explained force vertex and free vertex, and there I had explained V velocity into R is constant. That was velocity inversely proportional to R, and this was the free vertex. Hence the name is free vertex design, number one. Okay, this is the one conclusion you will have from the free vertex design. Like this, what is the velocity? Ct, Ct2, Ct3. If it is Ct2, then Ct2 into R2 is equal to constant. You can write Ct2 into R2 is equal to Ct3 into R3. Okay, so this is the one conclusion. Now we'll go for the second conclusion. What is the second conclusion? That second conclusion is nothing but the stagnation enthalpy. Okay, across the annulus, means with respect to radius, it is not going to change. So stagnation enthalpy across the annulus will be constant. Okay, stagnation enthalpy, you can write, this is nothing but dH naught by dr. Dr is the radial distance, and this is nothing but 0, or it is constant. This is the another very important conclusion. Okay, H naught means stagnation enthalpy. Okay, you can write stagnation enthalpy across annulus is constant. This is the second conclusion. Okay, now we'll go for third. We'll go for the third. Third is very well known for the this free vertex design also. It is the constant axial velocity. So you can write here third one. This is the third one. And what is the third one? That axial velocity with respect to radius, it is what? 0 means CA is equal to constant. What is the mean of it? Simple. The meaning is very clear that axial velocity across the annulus is constant. Yes or no? That's the mean of it. Okay. Now, so based on this analysis, okay, that axial velocity across the annulus, okay, this is the constant, or over the annulus, throughout the annulus it is constant. Okay, now CA is axial velocity is constant. Okay, this is the conclusion you got. Constant. This is the conclusion of free vortex design. Now based on this we have the that concluded result. Okay, and what is the concluded result in terms of degree of reaction? Okay, so that I will write and then I will finish it. So now final formula I will write here. So what is the final formula? So this final formula is, in general, we can get the degree of reaction over the blade. This is okay. This is the, if you know that in starting only I had given the radius. Okay, so this is the, you can say, R of hub, or it is also can root, and this is the what blade. Okay, anyway, and this will be the R tip. Okay, root and tip. Now R mean. Okay, anyway, and for the turbine, suppose, and this is the blade is given. Okay, anyway, so how to write the degree of reaction for any point? It is root or tip or mean, anywhere you can calculate. So what is the formula? In general, we have R RU is equal to 1 plus RK divided by RU. whole square RK minus this formula you need to remember. Okay. Where RK is radius at which degree of reaction is known. Are you radius at which degree of reaction is unknown means need to be calculated. Okay. Similarly, this RK is what? Known degree of reaction. Are you this one is degree of reaction need to be calculated. Done. Just for example, you can take any example. Suppose known degree of reaction we have at the mean, okay, and we want to calculate degree of reaction at the tip. So we can do that now with the help of this formula. What is the formula we have? Check. The formula is Ru, which is unknown, 1 plus Rk divided by Ru whole square Rk minus 1. Right? Unknown is tip. Sorry, U for unknown. Now we want to unknown means we need to calculate. Now I want to calculate at tip. So you will write R tip 1 plus K is what known. I am just considering known value is what mean. So mean is what known. So I can write R mean, and Ru is what unknown. Sorry, this is small r. Sorry. Okay, and this tip is what unknown, so tip square, and this degree of reaction, which is mean, is known. Remember, small r is the radius, capital R is the degree of reaction. Similarly, and for this mean is what known. Okay, if mean is known, okay, so what will be the value at root? R root is equal to 1 plus this mean is what known, this R at root So at tip you can calculate, at root you can calculate. It's your choice, wherever you want what to calculate, you can get that. Okay. All right. Done.